All right. I call this a velocity selector. I've read the problem here. It's basically an electron that comes in with some speed between two parallel plates. Well, if the parallel plates have charge on them, I hope you can see that this kind of configuration would create an electric field rather, that would travel straight from top to bottom here. Like you'd get field lines for the electric field that go this way. That would be E. Okay, this would be the velocity of the electron right now. And I want you to see something. This is an electron. Guys, how does an electron react to an electric field? Does it go with it or does it go against it? What do you think? Now, an electron has negative charge. Look at this equation and plug in a negative here. What do you see?
Wouldn't it go to like against the electric field because it goes to the point of highest potential? And
Of
the opposite
course. Of course. So you can see over here, just from this simple equation that connects the two, if you put a negative charge here, these are anti-parallel. So if the E is going down right now, you best believe that the force from the electric field will point up on this poor thing. So I'm going to put the forces, let me put this in green, particle in white, and the forces in red. So you're going to have a force from the electric field going up. Well, you can probably imagine here that I need a magnetic force that's going to balance this out. I definitely need an FB right now. It's going to go this way from my configuration right now. And, you know, for this FB to happen, considering the V naught is to the right, if you do the right hand rule where your thumb is this, your middle finger has to go down. Your middle finger. So the only direction for the magnetic field that makes sense right now is out of the page. You can check it out. Put your thumb along V naught. Put your index finger toward your face. And look at what your middle finger is doing. It should be pointing down. That's the correct configuration. Yeah.
George, the question says that the electron is in equilibrium, right?
Yes.
Right. So can we infer that from the electric field going down, that the magnetic field has to be going up?
The magnetic field is not going to go up. The magnetic force will be going in the opposite direction. Okay? Not the field. So
right, the force. That's what I meant.
Yeah, the field needs to go out of the page right now to cause this magnetic force, as you see. Guys, if I was going the other way, what would happen right now? Tell me right now to the force. What do you think would happen to the magnetic force? It would flip, wouldn't it? Because you're flipping again the cross product sign. That's what you're doing here. Remember, Lorentz force is, we're going to need that in a second. FB is Q, V crossed with B. So if you flip this sign of this, you're flipping the sign of the outcome immediately. And conversely, if you made this go in the X instead, you're flipping the sign of this. Again, you're flipping the sign of the force. So they all need to be mutually perpendicular. This, perpendicular to this, perpendicular to that. And they are. Okay, we've discussed again how we're going to get these forces going. Now, I already assume that there's an appropriate magnetic field in the area of the appropriate direction. So all I have to worry about are the sizes. And the sizes, the size of Fe is the size of the electron's charge, and the size of the field, the size of FB, is the size again of the electron's charge, size of its velocity, which is V naught, and then the magnetic field size. There's the sign over here is sine of 90. You know, like the V naught and the B are mutually perpendicular in this problem. So that will go away. We don't need it here. All right, you already see where this is going, okay? For equilibrium to be established, you need these two to be the same. So I set them to be the same, and that means the charge here will drop. I guess it doesn't hurt to just write it down. Just want to be a little faster though. Boom, boom. You're going to get here a relationship between the electric field and the magnetic field, as you can see. What does it ask? The plates are separated by 1 centimeter and are charged by a 200-volt battery. We'll get to why this is important in a second. It affects the electric field. What magnetic field strength and direction will allow the electron to pass between the plates without being deflected? So, what magnetic field strength? B equals to E over the speed of the electron. That's the strength that is required. Of course, we don't know what the E is, but we know that we have a parallel plate capacitor, folks. Okay. The separation of it, they said here, is S, let's say. And there is a potential difference also across it, which is given to you, delta V. You best believe that these quantities are related because the electric field, the potential difference across a parallel plate is the integral technically of E dot dl. But for parallel plates, because this is a constant field, the integral yields something very simple. It's just the electric field times the separation of the plates. So if you need the electric field, also this is a negative there, excuse me. From definition again, this is a negative at the front of it. So it yields E times S here. And so if I want the electric field from this, I take the potential across the plates and divide it by the separation. At the end of the day, you can see what happens here. The electric field is plugged back into the relationship for the magnetic field here. And we're done. That's the required magnetic field. What do you guys think?
Seems okay.
Seems okay, right? Balancing again electric force versus magnetic force. And electric force comes from Q times E, magnetic force from this cross product. E, you have parallel plates. You know how to find E from potential. Plug it in the last equation. Good with this one? Okay, that's the third problem out of the way. A little bit more on Lorentz force while we're at it. So I saw a very scary looking problem with these ones. I thought of covering it because I can tell it's going to be a troublemaker, but I don't know if I should do it later on in the next session. I just want to cover problems on every topic first. So let's see if we'll get time to look through this one. I covered a Lorentz force problem though. So technically, again, the topic, quote unquote, reviewed, but I want to cover more as the time permits. What about Biot Savart? Okay. I think the best one for the time being would be this one. So let's move it over here. What is the magnetic field strength at the center of the semicircle, it says here? Sure. You want the point to be right there in the middle. I'll bring in immediately the Biot-Savart law, which says dB is mu naught I over 4 pi dl crossed with r hat over r squared. Here we go. It's like the equivalent of Coulomb's law in magnetism. Okay. I want you to see how much the wires here and here would contribute to the magnetic field at P. So let's pick a random spot right there. That's called DL right now. And I want you to see that that spot of the current carrying wire, we can draw an R vector that connects it right back to P. Okay, that will be your R vector right now. Remember that the Biot-Savart law, the R hat, you can also write it as the R vector divided by the magnitude, and that magnitude can be absorbed here to be written as cubed instead. So you can write it also like this, be flexible. Why would I want to write it like this? To demonstrate right now this cross product. What do you observe about this cross product, folks? Take a look over here and tell me what do you think these should give you?
They're
They're
parallel, so
parallel.
they should be 0.
They give 0. That's right, Jeffrey. So it was Jeffrey that spoke, right? I didn't hear very well.
Yeah.
Okay. So this cross product is 0, done. You don't need to like talk about this at all. It's done. It's over. No magnetic field contribution from any point along this. Nothing. You can imagine that the symmetric aspect over here applies still, but it's a little bit different because DL and R are actually here in this case anti-parallel. But who cares? Both parallel and anti-parallel cross products all yield 0. So both this and that will yield 0 on either side. That leaves you with a semicircle now. I hope you can see. And yes, that is the only one that will have something to say here. All right, let me get rid of these because we're not going to care about them. We only want the semicircle now. All right, so for the semicircle, folks, I can pick up a random spot to put the DL, as I always do. Here it is. And then I'm going to connect it to the middle, but look at the size of the R vector all of a sudden. Seems like it's exactly the radius, isn't it? Convenient, right? This is the R vector. And as we do the integral across the semicircle, I want to emphasize that this R vector does not change in size. As we integrate the DL throughout the semicircle, it's always R. So the size of R, the vector here, let me write it like this. The size of it is capital R. Sometimes we write that without the absolute values. It just looks like this. Okay. Now, what coordinate system is good with curvy stuff? What do you think? Should I use Cartesians or something else?
What, polar?
Polars might be good, right? So with polars, the benefit here, guys, is that you have an angle that describes this position of the DL, and you can vary that angle easily to cover the integral that you need from 0 to just pi over here. It's so easy for the bounds as well. So what do I need? I need right now what DL is. Let's start first as a size. Well, the DL is pretty easy to find in polars. You just use the arc length formula because you know that this is R. Both of these extents here are R that I'm drawing right now to it. So I think you can see that the if the opening angle is d phi and these radii are both R, I think you can see that the size of DL, arc length formula, will be R d phi. Very nice and convenient. Okay. So, all right, R is equal to the capital R, DL is equal to this. What is its direction? Well, its direction right now, you know, in polars, this is positive phi. and this, well, the direction of the unit vectors changes all the time, but at that spot right there, this is plus phi, going counterclockwise, and the plus r is moving away from the origin right now. That would be the plus r. And you can imagine that these rotate as you go around the circle. They look different. But I just showed them there for a second. Meaning that if dl is going in the clockwise direction, it's going against this, and it's actually, as a vector, over here, we would put negative phi hat. Okay. Well, what about the r, curly r rather, as a vector itself? Well, the curly r has some size and some direction. I can clearly see that it's pointing toward the origin. That is opposite to what the plus r direction indicates. So that guy is going to get a plus r, or sorry, a negative r hat. Because he points toward the origin instead of away. Okay. I want you to notice again that we already know what the size of this is. Okay. So it's very easy to just get the r vector out of the way. This is just capital R and then negative r hat. Easy. Okay. Now, what do I do next? Well, the important bit is the cross product between these two guys. It's pretty obvious. So I'm going to go for it. dl crossed with the r vector, not the unit vector. Well, that's going to get me now what? It's this guy right there being crossed with this guy right here. Cross product. So at the end of the day, you end up having an r squared d phi. The negatives cancel, and all you get is phi crossed with r hat. Okay, that's not bad. What is phi crossed with r hat? Well, if you take again the coordinate system that I gave you at that instant in time right here, let's say that phi is going this way and r is going away from the origin, we said. Here. Phi at that beginning would be going north on that semicircle, and then r would be going this way. Okay.
It would be sine of 90, which would be 1.
It's not a dot product, but I'm looking, you see here, I'm looking to do it with the right hand rule. That's why I'm drawing it to you. Try putting your thumb along phi and your index along r. Open your right arm if you want. It's easier to do it if you open your right arm like you're waving hello. And put the thumb along like upwards, north, and put your index to the right, like you're shooting someone to your right. You should see your middle finger points into the page right now toward the wall. And that into the page is symbolized with this symbol, if you remember. Yeah, I can call this negative z hat, whatever. That's what they usually call it, but you can also leave it like that. It's the same thing. So this cross product is basically into the page. That's what it gives you. It has no size, because these are unit vectors. It only has a direction. There you go, folks. Cross product done. And you got to bring Mr. Biot Savart law here to finish it off. So we plug everything back in. The mu naught I over 4 pi is a constant, the current we have. The cross product, we found it to be this, r squared d phi, and then the cross product was negative z hat, the direction there. Underneath is the size of curly r cubed, but the size of curly r is capital R, so you're basically just dividing by r cubed. Good. And we've got some cancellation here. The next step would be integrating for that magnetic field. I see a factor of r popping outside right now. And your integral is over phi. Like I said, very easy bounds because, well, what would it vary between, folks? What would you take that angle from into? What do you think? Open it up with your eyes. That would be from 0 to what? I didn't hear that.
0 to pi.
0 to pi. All right, so that just gives me pi back. And that pi basically cancels this pi, and you get your answer. The magnetic field as a vector from the circle, which is the only thing that contributes anyways, is mu naught I over 4r in the negative z direction. And that is problem closed. What do you guys think? Covered okay? If they give you curved segments, it's only the segments that are actually curved that will make some kind of magnetic field at that center. Variations of this problem, for example, like from EC 106, you can see it probably here. Like, look at this one, right? You have this loop of wire, and you can clearly see that the R vector for this guy and the DL for that guy, they're parallel. So that cross product here will go away on that side. It's the same story if you look at the other R over here. That R versus, again, that DL, they would be anti-parallel at all times. So that side goes away, and the only sides that do matter are the ones that you see over here. Those are the ones that you would do the DL calculation for. You would integrate them from 0 to phi naught, right? The cross product would give you something. The setup is easy because that would just be the radius A for that guy, and the other one would always be the radius B for that guy. Easy again to do. It just has two curved segments instead of one like your problem had. Okay. You can squeeze it in the recording if you want. I give a lot of details here. You don't have to give that many details, but yeah, you can see what the end there will be like. I'll have it in the recording. Okay, so that's variations of that problem. What else? What else? What else? Going back to here, that's that. And then we have some other ones. Let me see. Again, I want to pick some that we can do within 13 minutes. Within 13 minutes, since I covered a Biot Savart one, again, I'm going to come back to these. I just want to do one of each, you know, so that we know we've done something. What about capacitance? You know, I think that should be a separate recording, though.